Welcome everybody. If you haven't had a chance to find a seat, you might want to grab one now before the fun begins. And my name is Carol Smith. I am the Dean of KU Libraries, and I really am glad that you are here for this fun, and as you will learn, far out evening at the Haricombe Gallery for our exhibit opening, which is entitled Pushing Boundaries with Science and Fiction. This is going to be an interesting talk. I am so delighted to see so many friends and supporters of KU Libraries here tonight. I do know that we have at least one Board of Advocates member, possibly more, but if they can make themselves known by raising their hands or standing. Lindy, you are our representative Board of Advocates member. Thank you for joining us tonight. For those of you who may not know, the Board of Advocates are an essential and dedicated group of library supporters who really generously donate their time, their insights, their resources to advise KU Libraries and to cultivate community awareness of all the connections and all the work that KU Libraries does, just like this evening. I've really been enjoying getting to know all of them personally and learning their affinities for KU Libraries and libraries in general. I have found that each Board of Advocate has a library story to tell. So if you do find yourself near a Board of Advocate tonight, and there's one, I encourage you to reach out and thank them for all the good work that they do on behalf of KU Libraries. So we are here for an exhibit opening. It's important to note that library exhibits require considerable time, considerable research, and considerable commitment to put together. They are truly a collaborative labor of love on the part of many people, not all of whom are always recognized. So I'd also like to recognize and with you express our shared appreciation for everyone who had a hand, whether it was large or small, in putting together tonight's exhibit and tonight's reception. So those of you, if you would like to raise your hands and make yourself known, all of you had a role. OCA, Sarah Thiel for sure. Thank you for all of the work that you did to make tonight possible. And, finally, I would really like to thank all of you for showing up tonight, because by showing up tonight, you are making tonight's event happen. You, whether you realize it or not, every individual here tonight is part of building communities via libraries. So thank you for being here and joining us. So as I am just beginning to settle into KU and all things KU Libraries, one of my great joys has been learning something new every day about the amazing and incredibly diverse work that our librarians and our staff do. And so I have been learning a little bit about the Haricombe Gallery itself, and I thought I might share a little bit of history with you for those who do not know. All of this happened prior to my arrival. So, and please, anyone correct me if I get this history wrong, but at some point around 2009, this area of the third floor of Watson was transformed into an exhibit space, and it was known at that time as the Library Gallery, and it was known as such for about 5 years. And then in 2014, it was rededicated and renamed the Haricombe Gallery in honor of Lorraine Haricombe, who was a dean who was just departing at that time after 8 years of service to the library. The Haricombe Gallery debuts 2 major collaborative exhibits every year, one in the fall semester and one in the spring semester, and I encourage you to come out again next semester for whatever that wonderful exhibit is going to be. But if you miss any, one of the things you may or may not know is that you can still visit those exhibits virtually. If you visit the library website, lib.ku.edu/exhibits, you can virtually tour not only this current exhibit, but past exhibits as well. And you will find such incredible and diverse topics that have been covered in the past, including public scholarship, indigenous wisdom, voting rights, government information, interdisciplinary scholarly work at KU on disabilities, and more. So I encourage you to visit those as well if you haven't already. So I would like now to introduce tonight Sarah Goodwin-Thiel to join me at the podium in just a moment to tell us more about tonight's exhibition, its connection to the KU Common Read book, Parable of the Sower, and to introduce our keynote speaker tonight, Dr. Ian Crossfield. Sarah is the Faculty and Community Engagement Librarian for the University of Kansas Libraries. She holds a Master of Arts in Library Science from the University of Missouri-Columbia, which we know affectionately as Mizzou. And she has a Bachelor of Arts with a specialization, and I didn't know this until I looked this up. She has a Bachelor of Arts with a specialization in studio art and printmaking from Southern Illinois University in Edwardsville. And I just met the library dean from SIU a couple of days ago. So as our faculty and community engagement librarian, Sarah works to foster an environment of engagement with KU and the broader community to cultivate outreach relationships and to forge really important connections that connects KU beyond our campus boundaries. And she has forged important relationships with the Lawrence Public Library, as I've learned with the Haskell Indian Nations University, and so many other important cultural and educational institutions throughout the region. She literally weaves community together, and I've really been enjoying getting to know her. Tonight is a primary example of weaving community together, and we do have her to thank for tonight's event. So please welcome, along with me, Sarah, to enjoy introducing tonight's program and our keynote speaker. Thank you, Sarah.
Hi. I'm going to crash Sarah's intro, if that's okay. You can stand here or you can sit, but very quickly, before she starts talking, I just wanted to give a little PN to Sarah. So my name is Samantha Bishop Simmons. I'm the Humanities Librarian here at KU, and I've worked with Sarah since 2018 as her dutiful assistant and helper putting these galleries together. And tonight, I just wanted to take a couple minutes to say a few words about Sarah. This is going to be Sarah's final gallery opening tonight, and I would just like to talk a little bit about her and what she has contributed through the Haricombe Gallery. So what can be said about Sarah that isn't universally known by everybody who works with her? How her kindness and curiosity, her warmth and intelligence, her quick wit, and even quicker hugs have shaped the culture of KU libraries. So if you've ever come to a Haricombe Gallery event and enjoyed a surprise connection with a stranger or a colleague about an esoteric topic, or if you've come away babbling excitedly about indigenous knowledge and medicinal plants, even though you're an electrical engineer and all of your friends are very puzzled, or if you found yourself knowing way more about the Spanish and Portuguese department than you ever thought you'd know and caring a lot about it, then you have been touched by Sarah and the gallery's impact. When I began working at the libraries in 2018, I was aware of the importance of showcasing interdisciplinary scholarship. I worked at the Hall Center for a long time, and I've had a lot of that experience myself. But I didn't understand the interpersonal alchemy it took to convince busy scholars and stakeholders of the importance of an event that captures the romance of what people think libraries do. The Haricombe Gallery is sort of a modern salon experience of sharing ideas and fellowship over the course of a semester, quietly demonstrating over and over again why the library is a beating heart of campus intellectual growth. With Sarah here, the emphasis is absolutely on the heart. The Haricombe Gallery is her brainchild, and it definitely shares a lot of family resemblance with its creator. So, like I said, this is Sarah's last gallery opening as she moves toward the promised land of retirement. Her shoes are impossible to fill, but sorry. I wore this suit because I wasn't going to cry because it's very strong looking, but my colleague, my mentor, and my friend, we would not try to fill them. We will continue in your honor and because of your vision, and when you're enjoying your loom and your new grandson and hopefully some boat drinks somewhere, we will keep the spirit of connection that you've created tightly woven. Thank you for everything, and thank you for the gallery.
Wow. I didn't expect any of these things, so thank you, Carol and Samantha. Any of you who have been to these receptions before know that I cry, but I'm not going to. I'm trying my best. So anyway, thank you all so much for being here, and thank you, Samantha and Carol, so much for your kind introduction and overview of the gallery. I'll just go straight into the exhibition introduction. Good evening. Welcome to all of you. Thanks so much for being here. My name is Sarah Goodwin-Thiel, as you know. I don't need to tell you too much about me, but as you've heard, the Haricombe Gallery is a space that promotes the creative scholarship of our campus community, highlights the strength of the library's collections, and works in partnership with cultural venues, internal and external to KU. The Pushing Boundaries with Science and Fiction exhibition was developed in conjunction with the 2023-2024 Common Book, Parable of the Sower. This is a dystopian science fiction novel written in 1993 by Octavia Butler. The exhibition highlights the research and creative work of interdisciplinary KU scholars who rely on imagination and forward thinking to address many of the environmental and social concerns prophesied by Butler in the Parable of the Sower. We are honored to showcase the innovative merging of science and fiction seen here at KU. The research and creative work of KU scholars serves as a foundation for expanded learning, access, and inclusion across disciplines. Pushing Boundaries highlights just a few of these scholars. Anthony Boynton, Department of English; Ali Brox, Environmental Studies; Masood Kalantari, Chemical and Petroleum Engineering; Junmo Kang, School of Social Welfare; Burl Oakley, Department of Molecular Biosciences; Paul Scott, Department of French, Francophone, and Italian Studies, as well as Ian Crossfield, tonight's speaker, Jonathan Brandy, and Alison Kirkpatrick, all from the Department of Physics and Astronomy, who are working with the James Webb Space Telescope. The researchers and others are supported by the J. Wayne and Elsie M. Gunn Center for the Study of Science Fiction and the extensive science fiction collections found here in the Spencer Research Library. You can find information about all of these people and units in the Pushing Boundaries exhibition that you'll see here in the gallery. I hope you had a chance this evening to sit down in the gallery and view the online exhibit. If you did not, or when you are ready to take another look at the exhibition, the QR code and URL on your program will take you to an online version so you can visit and interact with the exhibit wherever you are. As always, it took a lot of people to make this evening possible. I'd first like to thank the Haricombe Gallery program team, Assistant Coordinator Samantha Bishop-Simmons, Owen Murphy, and Kevin McCarty for their excellent curation and installation of Pushing Boundaries. Our Dean of Libraries, Carol Smith, thank you for being here at KU and for your leadership and support. All of our library colleagues who every day support KU research and creative work. And a special thanks to our partners in the Office of Communications and Advancement for their wonderful event management and promotional work. I would also like to especially thank our wonderful pianist this evening, Verla Winkelmolen from the KU School of Music. She did a beautiful job. Thank you so much for that. And now I'd like to introduce our speaker, Ian Crossfield. Ian leads the KU ExoLab, a research group dedicated to the discovery and characterization of nearby planetary systems. He is an associate professor in the Department of Physics and Astronomy. His interests lie in exoplanet formation, composition, detection, and characterization, and the development of instrumentation to further these pursuits. Dr. Crossfield is one of many scientists around the world who are working with NASA's James Webb Space Telescope. We're honored to have him here tonight and to learn more about his research. Please help me welcome Dr. Ian Crossfield.
Thanks, Sarah, for that introduction. Thanks to the whole Haricombe Gallery team for giving the chance to talk to you about the exciting work I'll be talking about today. Was amused to learn just this evening that Sarah is actually practically my next door neighbor. So I've been living 150 meters away from her for the last 4 years, but we only met tonight. That's the way the pandemic years have been. One other thing before I get going, just an amusing note, the gun center and science fiction have been mentioned a number of times. I'm a big fan of science fiction. I was really raised on it. A couple of years ago during the pandemic, when I had nothing better to do, I was digging through some old census records and discovered that 70 years ago, a 21-year-old James Gunn and his young family were living in my house. So I am actually living in James Gunn's old home, which kind of blew my mind when I discovered that. Okay, so what I'm going to talk about today is more, the theme of the exhibition, of course, is the melding of science and fiction. I'm going to be talking to you more about the science. The fiction, ironically, the fiction in the work that I do is all of these pictures you see here of planets. All these pictures, whenever you see a press release that says a planet outside the solar system has been studied, the pictures are lies, really. Or as my friends in the humanities like to say, they're art. Because what is art but just something that we've made up to try to tell a story? So all of the beautiful pictures over here hanging in the gallery portion, all of those are real pictures taken by the James Webb Space Telescope, except one, which is art. And what I'll mainly be talking about today is the abbreviated story of the James Webb Space Telescope, NASA's newest, biggest, bestest facility for observing the universe, and specifically what it's been doing for planetary science. Let's see. Only other thing, I want to thank a couple of members of my group. So Alex Polanski in the back can wave, and Yoni Brandy is up here, can wave, and Ashley Lieber in the back. Not in my group, but these are up-and-coming astronomy graduate students, so thanks for coming out as well. Okay. Okay, let's set the stage. So I call this 400 years in 40 seconds. So there will be a few plots. I'm a scientist, so I really like plots. I'll try to mostly show you pretty pictures, but a few plots. This is a plot just showing the size of telescopes by year. And down there on the left, in 1604, Galileo built a telescope. Just a little telescope, but it revolutionized the world of astronomy in particular and of humanity's understanding of its place in the universe. And that's just a little picture of a replica of his telescope, just a couple centimeters across. And the size of a telescope is important because the bigger the telescope, the fainter the things you can see, the further away things you can see, you can just study more things overall. And so as time went on, technological process slowly went along, and telescopes got bigger and bigger. And this shows William Herschel's 1804 telescope. It was about, I think it was a meter or two across. But it needed all this huge wooden scaffolding. It was a great beast. They called it the Leviathan telescope. It was very ungainly. Only pieces of it survive. It just was out there in the elements. People thought that cloudy Great Britain was a good place to be doing astronomy back then. We know better now. And so as time continued to pass, new, more modern observatories have been developed. This shows one of the leading observatories in the world, a number of telescopes up on Mauna Kea, the tallest mountain in Hawaii. And even if you're not a scientist, you can see that all of these points, the sizes of these telescopes, of course, this isn't all telescopes that have ever been built, but there's a general trend here. And as a scientist, I would say we fit a line to that trend. And what it tells us is the size of telescopes over 400 years has obeyed a remarkably straight and tight correlation. You've maybe heard of Moore's law, the idea that computer chips get better, get twice as good every 18 months. Well, this is like Moore's law for telescopes, except it hasn't just been over a few decades, it's been over 4 centuries. I'm not saying this is a law of science and that this will necessarily continue, but it's remarkable that this has gone on for so long. Now, all of these telescopes are on the ground. It's relatively easy, I say as someone who's never built a telescope myself, but it's still relatively easy to build a telescope that's on the ground. If something breaks, you can just go there and fix it. It's much more challenging in space. And of course, for most of the timeline on this plot, humans couldn't do anything in space. And so it's only been in the last, say 50 or 60 years that space telescopes in space have become a thing at all. And you can see that the rate of increase in how big they are has been much steeper. Space telescopes have gotten bigger faster than telescopes did on the ground. as our technological capabilities really ramped up very rapidly. And the biggest little star up there is the James Webb Space Telescope, or JWST, or Webb. You'll hear me use a couple of these terms interchangeably. That's the topic of our talk. So why are space telescopes smaller than ones on the ground? Because you have to lift them into space. And that's not easy to do. Whether you like Elon Musk or hate him, he's making it easier and cheaper for us to put telescopes into space someday. But you have to launch them, you have to design them. They're just generally overall more expensive. But when they get there, they can do better work. And so this is an actual photograph of the JWST's launch from French Guiana on Christmas Day 2021. So a little under 2 years ago. And against all of my expectations, I thought it was going to blow up on the launch pad, but actually, that would be a short talk then, the talk would be over. But actually it worked. And so this is not a real picture, but it's an artist's representation of what the observatory looks like today as it's out there sailing away several million kilometers away from the Earth. And after it went up there, about a 6-month checkout period, it started doing science. This is not a small undertaking, so it's not a small telescope either. So this shows these mylar sheets are what's called the sun shield. As I'll talk about in a little bit, it's important that JWST stays at very cold temperatures, and these layers of reflective, it's just like mylar, like the balloon you buy for your kid. And so they reflect the rays of the sun away. And you can see they're the size of a tennis court. And these are the number of engineers at NASA working on a test opening up and unfurling of this back in, I think, 2014. People have been talking about this telescope since the 90s. It's been a long process, a long, expensive process. Here's another real example. Now, this is the real, what we call the primary mirror. And I said the size of a telescope really depends on how much light it can collect. Well, JWST is actually made of a tessellation of these little hexagons. Each of them is polished beryllium metal coated in gold. And the whole thing folds up, and it's 20 feet across from top to bottom, so it's dwarfing these engineers beneath it. But lo and behold, it got up into space. It works. So we've had space telescopes for a long time. So why is JWST interesting? This is a NASA graphic that highlights one aspect. The first aspect is it's the biggest space telescope we've ever had. Up here on the top, you can barely see it in the upper left. That's a picture of this tiny little space telescope called Spitzer. Spitzer was a telescope observing at wavelengths longer than our eyes could see. And the little circle in the upper right, is proportional to how big its mirror was. Now, it was actually 2.5 feet across, so nothing to sneeze at. But compared to the Hubble mirror, hopefully you've heard about the Hubble Space Telescope, Hubble is bigger, and JWST is even bigger still. And you sort of see a side view of the telescopes themselves on the far left. So the bigger the mirror, the more light you can collect, the more distant the things are you can study. So Webb is the biggest space telescope we've ever had. The second interesting thing is that it accesses a part of the spectrum that we haven't had access to before. So all of us are familiar with visible light. You're seeing this presentation because your eyes are sensitive to visible light. But actually, visible light is only a tiny fraction of an essentially infinite spectrum of different wavelengths of light, different colors. Our eyes can only perceive a tiny portion of that reality. And so there's gamma rays, X-rays, ultraviolet, the infrared, microwave, radio, and it really extends on in each direction forever. So this again puts these are sort of NASA's most recent 3 big space telescopes in context. The Hubble Space Telescope is mostly sensitive to ultraviolet light and to visible light. It goes a little bit into the infrared, longer wavelengths, but not very much. That's really not what it was designed to do. The Spitzer Space Telescope on the far right here looked at wavelengths in the far infrared. So this is wavelengths where things like coal dust out in the universe emit a lot of light. You didn't know it, but actually all of us are glowing all the time. So you see someone because the visible light bounces off them, but actually if your eyes were sensitive to infrared light, you would see everyone's faces glowing. And things glow different amounts if they're different temperatures. So JWST sits right here in the middle. So it really plugs a gap in wavelength coverage between HST, which is still operating after 30 years, really remarkable, but it wasn't designed to last that long. It could fail any day. Spitzer Space Telescope is already defunct. It's not operating anymore. JWST is more sensitive than both, and it fills this gap in this wavelength coverage here. So that means gives us a unique capability to access all aspects of the universe that happen to give off radiation at these infrared wavelengths. What I'm mainly interested in, as you heard in the introduction, is planetary systems. So I'm going to talk. Let's talk now about what initial things has JWST been starting to do as far as planets go. So I promised you some pretty pictures. So you're back in astronomy class at university. What planet is this? Saturn, that's right. Okay, Saturn. So this is Saturn as you're used to seeing it, probably. This is Saturn at visible wavelengths. And this is a picture taken from the Hubble Space Telescope. It's very pretty. It looks very typical to what you're used to seeing from Saturn. So the difference then is here's Saturn now seen by JWST at infrared wavelengths. And the point here is that the infrared, by looking at different wavelengths of light, you learn different aspects about whatever object it is you're studying. So one thing you might notice here is that those prominent bands on the surface of Jupiter, not the rings, but the surface of Jupiter itself. Do I have a pointer here? I do. Okay. So all these bands on Jupiter really don't show up much at all in the infrared. That's because the infrared is more sensitive to the temperature of things, whereas the visible is more sensitive, in this case, to the sort of whatever surface pollutants are sort of discoloring the surface of Venus. You also see here that the rings are much brighter proportionally to the surface of Saturn. And that's because the rings, just like the surface of Saturn, are glowing at infrared wavelengths. And actually, these rings are, the wavelengths that this image was taken at was where the rings are really glowing and giving off most of their radiation. And so it lets us learn things about what's the distribution of sizes of the little particles that make up these rings, what's their typical temperature, what might they be made of. You also see a few other little dots that you think, oh, something's wrong with the projector, but those are actually real things too. So those are some of Saturn's moons. And they also show up much more clearly in the infrared than in the visible, again, because Saturn is much farther from the sun than the Earth is. Saturn is colder. And so these planets they don't glow at visible wavelengths, but they do glow in the infrared, where JWST is observing them. So another example is if we go out from the solar system, the next planet outward from Saturn is Uranus. And so this is a picture taken about 6 or 8 months ago by JWST of the Uranus system. And so you can see the planet here and what looks like a field of stars scattered all around. Most of these, all the labeled ones, are again all individual moons of Uranus. And this is the clearest view that we've had of the Uranus system in the infrared since the Voyager probes went by in the late 70s or early 80s. And so a zoom in here shows that here, interestingly on Uranus, we actually do see, it's not a sort of uniform featureless disk like Saturn was. There's actually, at least some sort of features here that indicate these bright regions are storms in the atmosphere of Uranus, where the winds are sort of cyclonic winds like Jupiter's Great Red Spot. And it looks brighter because JWST is able to look deeper through the clouds into the deeper, hotter interior. So we're able to learn something about the global temperature structure of this planet. Uranus is an interesting planet for lots of ways. It's the only planet that lives its life on its side. It's also going to be the target of NASA's next big solar system probe. We've sent probes to Venus, many to Mars, Jupiter, Saturn, and so the next big plan in sort of the next decade or two is sending a big probe out to Uranus and study it, because it's a member of a class of planets we really don't understand very well yet. If we keep going on out, we've got Neptune here. So what looks like some bizarre artifact up here is actually just Neptune's big moon Triton. This you can ask me in the Q&A why it has this sort of fairy butterfly looking structure. But anyway, it doesn't really look like that. It's just a moon. And here's Neptune. It looks a little smaller because Neptune is further away. So even with a big telescope, there's a limit to how well you can resolve it. But again, these are some of the best images we've been able to acquire of Neptune We have ground-based telescopes, but they just can't compete with JWST's sensitivity and its ability to resolve very fine details. And you can also see the rings. We always talk about Saturn as having the planet with the big rings in the solar system, but actually Neptune has rings too. I didn't point it out, but Uranus obviously has these big rings as well. And they also show up much more prominently in the infrared than they do in the visible. This is a compare and contrast now. This is Uranus on the top and Neptune on the bottom, as you might be used to seeing them, assuming you think about these planets at all. I do a lot. And the Webb infrared view on the left, and the Hubble visible light wavelength image on the right. And so you can see that although some things kind of look similar, sort of light spots, light regions, darker regions, other things look dramatically different. And in particular, the thing that sort of jumps out at me the most when I look at these is how much more visible the ring systems of these planets are. Rings are typically made of, like the Saturn's rings, they're made of icy chunks of this and that are left over from, we're still not precisely sure what. But as often it's not pristine, pretty, bright, white snow and ice. It's dirty, sooty, dusty junk covered with all sorts of organic molecules. And so they're often very dark at visible wavelengths. You really can't see them in the Hubble Space Telescope images at all here. But it doesn't matter what they're covered with, because in the infrared, they're all glowing. And JWST, by being sensitive to that infrared light, is able to directly study them in this way. And so that will tell us more about how these planets might have formed, how their moons might have gotten there, and sort of putting our whole solar system into context. We can't point JWST at the Earth because the Earth is too bright, and because it would be pointing too near the sun and it could just fry all of its detector arrays. But we can look at the planets here in the outer solar system. So these are just some sort of pretty pictures, but really I think JWST's strengths lie not in taking pictures, which any old camera can do at some wavelength or another, but in spectroscopy. So deep science dive for a moment. If you hate science, put your fingers in your ears for a moment. Spectroscopy is the process of taking light from some distant object. It could be a galaxy, a star, another planet somewhere, and JWST collects the light. And essentially, you can think of this as just filtering the light through a prism. We're all familiar with the idea that if you take sunlight and split it through a prism, it turns into a rainbow. Well, it turns into a rainbow of visible light because that's all our eyes can see. But actually, you can make a prism that splits the infrared light, like a prism as well. And if you can do that in a sensitive and controlled way, you can actually look at the individual fingerprints of different materials. Like here's a couple examples of atoms of carbon or nitrogen or oxygen or iron. Each of them have their own unique fingerprint in the spectrum of the light. And so in a picture, if you look at a picture, you could say, well, Neptune and Uranus from these pictures could be made of anything at all. Green cheese, I don't know. But if you can point a spectrograph at them and take a spectrum, then you can really start to learn what an object is really made of. And so that's most of the most powerful work that JWST is doing comes from its ability to take spectra of objects, not just images. So a familiar planet, this is now a spectrum of Mars. And so what is in a spectrum? Basically, you're just measuring how bright is the light on the vertical axis and what's the color of the light on the horizontal axis. You're just measuring how bright are the different bands of the rainbow in infrared light. And Mars is a nice test case. It's a sort of fiducial reference point. We've landed tons of spacecraft on the surface of Mars. We understand it inside and out as well as any other planet aside from the Earth. So by pointing JWST at it, it's a way to sort of calibrate how well do we really understand Mars and how well does JWST really work. And, of course, it works great or I wouldn't be giving the talk. I would have picked a different topic. And, but what you see here is each of these sort of different regions where things get to where they step up or step down. They're color-coded and labeled here on the top. But there's just lots of different features in the spectrum of Mars that show us that it's mainly an atmosphere of carbon dioxide. There's lots of these big troughs where the line goes down toward the bottom, where molecules of carbon dioxide absorb. And That's good because we know Mars's atmosphere is mostly made of carbon dioxide. It doesn't have much of an atmosphere, but most of it is CO2. There is a little bit of water vapor. We keep talking about, is there life on Mars, or did it once have oceans even though now it's dry? There's still tiny bits of residual water vapor in the atmosphere. That's not a surprise. A fun astronomer drinking game is every time NASA comes out with a press release saying we found water on Mars, everyone takes a drink because it feels like every couple of years that we found it again. It keeps people interested, so that's good. But we know there's water on Mars. That's not a new thing. It's even on the moon. That's been found many times as well. So we can do the same thing. In essence, we can do the same as this, but we're now going to shift gears slightly, and now we're not talking about Mars, the nearest, most Earth-like planet in our solar system, even though it's not a very pleasant place to be. We're now going to step outside of our solar system. I'm just going to take the last few minutes talking about what JWST has started to reveal and tell us about planets in other solar systems. If you hadn't heard that, there are other solar systems. There are other planets, and they don't orbit around our own sun. There's lots of them. We know about thousands of these. And we're able to finally study them in ways that we were really never able to do that before. So this picture here is, in some ways, in many ways, maybe a more complicated spectrum than the one of Mars I was just showing. But this is really the first high-quality spectrum of an exoplanet that JWST has taken. And this is from a big international collaboration of hundreds of people that Yoni and I are both involved in. And each of the sort of vertical colored regions here just sort of highlights all of these different molecules and materials that we think are in the atmosphere of this planet. The planet is called WASP-39b. Astronomers are not good at naming their planets. But anyway, there's all sorts of interesting molecules here. Not only is there water vapor, that's the sort of one molecule we had been able to probe with the Hubble Space Telescope before, but actually there's lots of other materials in there now as well. There's carbon dioxide, just like we saw in Mars's atmosphere. There's also carbon monoxide, also CNO, but in a different molecular configuration. There's atomic sodium just sort of floating around in the atmosphere of this planet. This planet is even hotter than Venus, much hotter than the Earth. So it's a very different kind of atmosphere. It's more like a gas giant than a rocky planet like the Earth or Mars. And there's sulfur dioxide here as well. And let's see, I think that our... carbon monoxide had been seen by ground-based telescopes before, but definitely carbon dioxide and sulfur dioxide are this spectrum, this team's analysis here, are the first times these molecules have ever been seen in a planet outside the solar system. Carbon dioxide was sort of expected, but the sulfur dioxide, SO2, and that's part of what makes smog, was really unexpected. It doesn't mean that this is, there's smog aliens there. It actually, just to not walk you through chemistry class again, but it tells us something about what's called photochemistry, which just means chemistry that's catalyzed by incoming high-energy photons, light, from the star itself. This is a type of chemistry that many people have talked about for a number of years in these extrasolar planets in other solar systems. But this discovery of photochemistry was really the first unambiguous detection that this photochemical process is really going on. And through this chain of reactions that we're not going to walk through, ultimately creating sulfur dioxide. And in a recent paper, I talked some about how by being able to access this sulfur dioxide, we might actually be able to learn a lot about the particular ways in which these planets formed and accreted their gas and solid materials. That has to be tested. So I'm going to skip that in the interest of time. I will just mention that JWST is not just studying these gas giant planets like Uranus, Neptune, this WASP-39 one. It is also looking at rocky planets in other solar systems. And so one of these that's been very popular is called TRAPPIST-1b. There's actually 7 planets in the TRAPPIST-1 system. TRAPPIST because it was a forced acronym about the TRAPPIST beer. So astronomers like their forced acronyms also. Anyway, TRAPPIST-1b, the innermost planet in the solar system, sort of that system's Mercury, doesn't seem to have an atmosphere. But there are 6 other planets in the system, and JWST is continuing to pursue observations of those other planets as well. Analyses still aren't completed there. So it's really, it would be better to be giving this talk a year or two from now, because JWST started doing its observations a little over a year ago, but really acquiring the data, learning how to process it from a new facility, learning how to interpret it, like having to search for these new theories of how to understand these photochemical processes and other processes like that. There are still only sort of smattering of interesting, compelling, and I would say conclusive results that have come out of this analysis. Well, I will show this one because this is one of them, I think. This is just another spectrum of a weird planet that no one except one guy, who I think is too far out there. It's not even an astronomer joke. I mean, he really is. But he's been talking about these planets that would sort of be half ocean, half gas giant planet. And it sounds kind of weird, but the result is that the spectrum shows no water vapor at all, because even though there's a lot of water, it's buried under the hydrogen envelope. So all you see is methane at the short wavelengths and carbon dioxide at long wavelengths. And maybe there's some tentative evidence for some other interesting molecules, but that's pretty tentative, so I'm not going to talk about that. So this is an example of it's another gas giant planet. There's no solid surface that you could walk on, but it's another weird kind of planet with weird physics going on that really hadn't been predicted or at least accepted in the mainstream, but seems to be a real deal. And this is what happens every time astronomers build new telescopes. We're surprised by what we find, and although we try to come up with ways to explain, we think this is why we should build it because we'll find this. In my opinion, the real reason is just because the universe is out there and we're going to be surprised and find something new every time we look at it. So JWST didn't just spring into being fully formed out of someone's forehead. It was the process of it was an endpoint of a long process of not just construction, but planning. Every 10 years, astronomers go through what's called a decadal review, a community-wide national project to assess our priorities so we don't all just kill each other with internecine warfare and we can actually unite around a common goal. JWST was one of those goals as identified in decadal surveys of several decades ago. This is the cover of the most recent one. We called it Astro 2020, or Pathways to Discovery. That's where I stole the title from my talk. And this, the motivation, the top priority, the first mentioned priority of this goal, there were 3 goals, but the top one was something called Pathways to Habitable Worlds. There's a lot of clickbait out there in science journalism. And so it's very easy to find a science article that says life discovered on a new planet, and you're not an astronomer, so what do you know? I can just tell you the next 8 press releases you read that talk about life on another planet, at least outside the solar system, are wrong or exaggerated. There's just it's like the supermoon. It used to just be there's a full moon tonight. Now it has to be a supermoon. It's like grade inflation, I guess. Anyway, we do have the capabilities to conceive of how to build a next generation of telescopes that might really be able to tell us about habitable worlds, planets that could be like Earth in terms of size, temperature, presence of liquid water on the surface as a precondition for life. There's a vast array of NASA exoplanet missions, both some observatories on the ground, small little tiny CubeSat missions that are just run by universities, medium-sized ones, and big ones like Hubble, Spitzer, JWST. By the end of the decade, we expect the Roman Space Telescope, Nancy Grace Roman. And after that, talking 2040 to 2050 sometime, we're now talking about how we could build something called the Habitable Worlds Observatory to find and characterize the atmospheres and maybe the surfaces of these worlds. So I hope I may be retired by then, but we'll see. It's a pretty exciting prospect to look forward to, but it's a long process. But this is our pathway to discovery. So with that, I don't want to take up any more time. I just want to shamelessly plug 2 sets of events. There's a couple handouts out here by the check-in table. One of these, this is our public astronomy outreach calendar. We've got events every month. So you can just pick up one of those out there. But basically, it's every month on the 3rd Thursday over by Malott Hall. And then in particular, our one coming up in just a couple weeks, Ashley made this flyer. You maybe didn't hear that there's an annular solar eclipse that's going to come and hit Lawrence, Kansas. And so we're going to have this is October 14th, starting at 11 a.m. out on the Malott Hall lawn. you can pick up the material there. All right, and with that, I think I will just leave it back up here. Thank the organizers again, and you all for listening to this talk. Appreciate it.
Does anyone have any questions for Dr. Crossfield?
Of the planets that we know enough about, what would be the percentage of rock-like planets as opposed to gas giants or whatever else are out there?
It's a great question. The question was, what's the relative frequency of rocky planets versus big gas giant planets? We think that it's tough because the smaller a planet is, the tougher it is to detect. And our capabilities have only sort of scratched the surface on the rocky planets. I think it's fair to say that rocky planets are more common than big gas giants like Jupiter. But there seems to be this new class of planets that I alluded to that spectrum there, that's sort of intermediate in size between Earth and Uranus and Neptune in the solar system. We don't have any planets like this in the solar system. And they seem to be really common too. But we don't actually have any right here in our local neighborhood. And if specifically you're thinking of not just rocky planets, but rocky planets that are the right temperatures, that they're maybe similar to Earth, we really don't know that answer yet. There was a mission that finished up a couple years ago called Kepler that told us it's probably on the order of maybe even 10% of stars like the sun have a planet kind of similar to the Earth. Might not have water, but it could. But there are big uncertainties on that measurement.
How far away are these exoplanets?
The question was, how far away are these exoplanets? So they are very far. Space is big, really big, and it is the nearest, and yet the planets are everywhere. So the nearest star to the solar system beyond the sun is the Alpha Centauri system. And we know from our ground-based telescopes that there are planets in the Alpha Centauri system. Most of the ones we talk about are further away than that, but even that one is a little over what we call 4 light years. So we think of light as instantaneous, but it takes time to travel, and it's a long way away. It's not something any of us are going to, and it's really not something we can plausibly even send a little robotic space probe to go and visit. Although some people and eccentric billionaires do talk about ideas, but it's a long way away. That's why the telescopes are so important. It's our best way to study them.
I'm curious, you showed us a picture early at the beginning with a moon that was looking very fairy-like, and you said that you would explain that to us.
Oh, that's okay, right. So in a nutshell, let's see, yeah, I shouldn't have invited the question, you're right. In a nutshell, that pattern just shows up there because of the shape of JWST's mirror. Because it's not, like if you go out and buy a telescope for yourself or something, the mirror in the back or the lenses are just circles. And so that doesn't induce too much sort of spurious visual effects in what you're looking for. But because JWST's mirrors are hexagons, and not just one hexagon, but a whole bunch of them, the way the light waves interact in the telescope can result in that sort of pattern. You can think of it as a fancy sort of like lens flare, if you're into sort of artistic photography or something like that. But it's just an artifact, it's not a real thing.
I am curious, but I saw something on PBS maybe about a woman who was doing Webb telescope art versions of the photographs. And I wonder, we were seeing some of these that are just photographs, and they're so stunning and gorgeous. And I'm wondering, what do you think, where does that come from? That does it make it more accessible to people to have an artistic version, or do you have?
No, I think it definitely for laughs, I kind of downplayed that a bit, but it is essential in making it more accessible. You might wonder, he showed us pretty pictures of the solar system's planets, but these really interesting ones in other solar systems, he only showed us these unintelligible spectra. Why didn't he show a picture of those? And it's because because these things are so colossally far away from our solar system, we can't take pictures of all but a very small handful of these planets and other solar systems. At best, we might see them as a few pixels of light smeared on the camera here. So you can either show people some blurry pixels and try to get them excited, which is tough in this day of TikTok and camera filters and I don't know what all, or we engage through the medium of art. And so I have no beef with it.
Oh yeah, I mean, it's a wonderful crossover, I think.
We know the universe is expanding. We know the universe is expanding. Is it expanding fast enough that, for example, the JWST would not be able to see as much in 20 years as it can now because things are further away?
Good question. The universe is expanding, but luckily that expansion doesn't happen on a local scale. So the distance from us to the sun or from us to any of these exoplanets, that's not really affected by the fact that the universe is expanding. That really only affects things that are not just a few light years away, but millions or billions of light years away. And so it's important on the scale of other galaxies, but not of other planets. The expansion is happening at a gradual enough rate that even by the time JWST runs out of fuel in 15 or 20 years, it won't really have been affected by the expansion of the universe.
Questions about how far away, the 3 or 4 that you specified, the exoplanets. So they're further than 4 light years away. Are they more like 100 or 1,000? But they're still a tiny part, a really tiny fraction of the Milky Way that we're actually looking at?
That's right. I'd say hundreds of light years typically. Some closer, some further. But yes, as you say, that even that distance, which humans can hardly hope to cross, is still just a tiny fraction of the size of our galaxy.
Is there anything like specific that the James Webb Telescope is looking at like nowadays? I know that it takes images like a lot faster than Hubble does. So like, is there like a specific area that like eats up all like the time that James Webb has? Like, is it like really focusing on something in particular, or is it just kind of popping back and forth like?
It has a wide range of science goals. So I only talked about planets here really, but it has sort of 4 overarching science goals. Only one of those is the study of planetary systems. So it's also spending plenty of time studying other galaxies beyond our Milky Way and all sorts of other phenomenon. And what it spends its time on is not really sort of just set down by diktat by some sort of autocratic telescope director. It's just, it responds to the desires of the community. If all astronomers were saying study exoplanets, then it would basically only be doing that. But there's lots of people studying lots of things, and so it does a mix. It's reasonably responsive.
Thank you.
Okay, thank you.
Thank you, Dr. Crossfield, for that wonderful and far-out discussion. It was a great evening. We're all fascinated by Webb and those images that we see. Just a few closing remarks. First, we are going to risk a few possible tears and ask Sarah to join us back up at the front for just one moment more, Sarah, if we can. We here at KU Libraries and everyone in the audience would really like to thank you for, is it 2 decades? 2 decades of service to KU Libraries and the community, making events like this happen at Haricombe Gallery semester after semester. You have brought love and light and learning to the community, and we are so grateful for all of your service. Thank you. Always visit. We expect that.
I don't live far away. Thank you so
Thank
much.
you.
Thank you so much. Yeah, a student of mine a couple of years ago, I think that was in 2018 perhaps, did a tally of all the faculty and staff and students that we had showcased their research in the gallery, and it came to like 236 people. It was just so many people, and it was really fun, and I have found over the years that every time you reach out to someone on campus to say, can we showcase your research in the library? And it's just like, yes, people are always so excited and so happy to do that. And it's been, we decided, Lorraine Haricombe, our former dean, had this idea that she wanted to have a gallery in Watson Library that would not just showcase library resources, but would showcase what KU is, the research that was being generated at KU that was contributing to anything that was happening, different things that were happening in the world. And so we started just showcasing and promoting and creating an easier access to research. And it was not a hard job, and people were very interested in sharing their research. And there's just not been a topic that we haven't found a whole range of disciplines that are people who are publishing. And so the different disciplines, sometimes people would meet each other for the first time because the people in musicology wouldn't know that the people in engineering had an interest in the same thing, with looking at it from a different aspect. So that's been so exciting for me. So it's been an honor for sure to be a part of this, and for the libraries to have supported something like this from the beginning was really great. I know that we had it's always been a huge team effort, and the committee that designed this space within this open study area, graphic designers and people from all over campus who helped us with the quote on the wall and the Haricombe Gallery logo. And I can remember reporting back to our administration team that our committee had decided that we should take all the panels, all the ceiling tiles off and expose all the ductwork and everything. And Lorraine was just like, we can do that. And Kent Miller, wherever you are, was just like, let's talk about that later. And so that didn't quite happen, but we were able to put together this gallery that was sort of a space within a space with no walls. And I think that's always been our goal, was to just have it open and creating very accessible scholarship, access to the scholarship that's generated here at KU. So it's been an honor for me, and I so appreciate all of this. So thank you very much.
One of the focal points of the Haricombe Gallery exhibits is interdisciplinary connections. And if you didn't already notice, just over there we do have copies of this year's KU Common Read, Parable of the Sower, available for you to take with you, to read, to enjoy, to think about those interdisciplinary connections with tonight's talk, because you will find them. And I love the title of tonight's talk, Pushing Boundaries, because that is exactly what libraries do. Libraries help all of us push boundaries and think in new ways and new perspectives. And so if you found that tonight helped push your boundaries, I encourage you to stay a little longer tonight, linger, visit the exhibit, talk with Dr. Crossfield about those interdisciplinary connections and the amazing photographs that you saw tonight, and help push those boundaries further out for all of us. And if you enjoyed tonight, I would also always encourage you, if you are not already a friend of KU Libraries, I would encourage everyone in the audience to consider being part of making events like this happen tonight. We always rely on the generosity of our donors to help keep events like this going. So thank you, and we will see you again next semester.